Okay, so previously, if we were sketching a polynomial, we would get the intercepts and the end behavior, and it would look something like this. Let's say we're doing a degree 4. That's what we are going to do. It's not the same one, but that's fine. What values would I know? I would know this value, 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 and I would know this value, the y-intercept, and I would know the end behaviors and the degree, that kind of thing. If there was a turning point like, or a twist like that, or a turning point x-intercept, we'd know that. We'd know that it was that kind of an x-intercept. So those are the details that we would know. But now with our skills around derivatives, we can add to that. So we can find, whoop, I shouldn't have erased that. Let me put it back quickly. Okay, we can find these points exactly as well, so we can have a bit more of an accurate sketch. And those are important points because there's something interesting happening there. So those are good points to have. So let's get to it. So first thing, I'm going to factor this. X squared minus 9, x squared plus 1. Good thing it's factorable. That's how we find the x-intercepts. X plus 3, x minus 3, and x squared plus 1. So we've got two x-intercepts. We've got a y-intercept. When x equals 0, because it's in standard form, that's easy. It's going to be -9. And then my x-intercepts occur when y equals, what am I doing? Equals 0. And so those happen at plus and minus 3. And that's it. Only those two. Because x squared plus 1, that's never going to be negative. So, or never going to be 0, sorry. So that doesn't help us out. So we got two x-intercepts. So we've got the intercepts done, all of them. Now we're going to go to the critical values, the other critical values. And for that, we need to know the derivative. So we go ahead and take the derivative. And we're going to factor it as well, because that's what's going to allow us to find those values. Okay, we can start building our chart. So we've got our x intervals, f prime and f. And the first one is going to be when x is less than -2. So this is coming from the factored form of the derivative. Tells me when there's some kind of local max or local min, or when the derivative is 0, right? Which will occur in each of those locations. So I pick a value to represent that interval. I pick -10, and I get negative times a negative times a negative, so they're all negative. So this is decreasing here. Now, this is where you might start to get yourself confused. I know that this is a cubic, and it's positive leading coefficient, so it would look like that. So it's increasing to start, but that's not the graph we're talking about. We're talking about f. So if I sketch some kind of an f, this is a positive leading coefficient, degree 4 polynomial. Look, it is decreasing. Like, that matches what we already know about that function, and that's great, but I won't always know that. Polynomials are easy, but there's other functions that aren't, so we still do need to do this interval testing, even if we kind of knew already what was happening there. At -2, we've got 0, and then from -2 to 0, I pick a value to represent that. So I'm going to pick -1, so I get negative, positive, negative. So two negatives makes positive, and it is increasing here. If it's decreasing and then 0 and then increasing, I can see that we have a local min. And I want to figure out where that local min is. So I am going to find all these values. And again, I'm looking in the actual function we're sketching, not the derivative here. I'm plugging all three of these critical values in to the original function. And I believe we get negative 25. This one's easy because it's the y-intercept. We've already done that. And negative 25. Okay? So just evaluating them, probably in there, whichever one's easiest. And then we can move on. So at 0, the derivative is 0, and between 0 and 2, pick a value to represent that interval. Pick 1. I get positive, positive, negative. So it's negative. So it's decreasing. So it's increasing. It's 0 and it's decreasing. Well, that's a local maximum. And that one is at 0, negative 9. Now we're starting to paint a picture of what this curve looks like. So at 2, it's 0, and when it's greater than 2, I pick a value, pick 10, positive, positive, positive. Whoop. And so it's increasing. And so I was, again, decreasing, 0, and increasing, so it's a local min. And I've already figured out what that point is. Oh, negative 25. Okay, I think we have all the information we need. I think we have all the details. Now I can go ahead and start sketching, thinking about what this is going to look like. I can mark the x-intercepts. Okay, so my x-intercepts were negative 3 and 3. Try to make those somewhat even. 3, negative 3, and we're not worried about scale. This is a sketch, but we list those critical points at negative 2 and negative 25. So this is negative 2. I'm going to put a point way down here. This is negative 25. And then another one here. This is positive 2, negative 2, and I'll just add those in. And 2 and 25. Let's see, 0 and 9 was an important point as well. And is that all of them? So we start up here. And there we go. And this one I forgot to label it. Negative 9. So we've got our picture. We know exactly what's new is we know exactly where these points are and where that point is. We're not just guessing. And then we still have all of our intercepts. And that's that. So that's a sketch. We've got everything that we need. We've got the intercepts, we've got the critical values. We've labeled everything. Well, actually, I haven't labeled everything, but let's go ahead and do that. Okay, make it look nice. I've labeled my critical values, just shown where they are on X, where they are on Y, and that's it for that one. Okay, so we're going to do one more here, and these ones that I've chosen here are pretty simple to factor. Like, these are kind of easier ones because, you know, they factor nicely. They're simple that way, but there could be some more work. We might have to do some like long division or something. Probably not long division, but synthetic division to factor these. They're not all necessarily going to work out, but just to save us some time for the lesson so we can see the more interesting new parts is what we're doing. So I can factor out an x cubed, and I'm left with x squared minus 15. Is that right? Perfect. And so my y-intercept is 0. So there's going to be a point at 0, 0. And my x-intercepts are at, like, I could show this. This is not something we see very often, but, right? It's like a difference of squares, but it's just not a perfect square. So I would still take the square root of 15. So my x-intercepts are plus or minus the square root of 15, which is about 3.9. Okay. All right. So we got that done. We can take the derivative. 5x to the fourth minus 45x squared. And again, I'm going to factor this. So I can pull out a 5x squared, and I get x squared minus 9. And so see how this one factors pretty simply. There we go. And we can start building our table. So when x is less than -3, I got -3, +3, and 0, again, is my values here, at -3, between -3 and 0, and then at 0, between 0 and 3, and then 3, and then when x is greater than 3. So these are where the derivative is 0. Oh, just thought of something. I didn't mention this last time. Because these are polynomials, we don't really have to worry about it, but I do have to f prime of x exists for all x, right? So there isn't anywhere, if this was a different function, we also have interesting things happening when a derivative does not exist. So that could be a local max, a local min, it could be an asymptote, it could be lots of things. And so we have to consider it. But for a polynomial, that's not going to happen. But we should state it because it's going to be relevant soon. So pick -10 and I get, looks like positive, positive, positive. Sorry, positive and then 2 negatives, which gives me a positive. So it is increasing to start. And if I pick -2, I get positive, positive, negative. So it's negative, so it's decreasing. If I pick 2, I get positive, positive, negative. So it's decreasing. That's interesting. And if I pick 10, I get positive, positive, positive. So it's increasing. So if it is increasing, then 0, then decreasing, that's a local max. If it is decreasing and then 0 and then decreasing again, that's a twist. We did see this. So this has neither a local max or a local min. It's a twist. And that is at the point 0, 0. And then decreasing, 0, increasing is a local min. And those points, so let's go back up here, f at -3 is, I believe, 162. It gets quite big. And f at +3 is -162. Just plugging them into our original function. And we already have f at 0. We don't have to do it again, but there it is. So this is a max at -3, +162 local max, and this is local min at +3, -162. And again, I think we have all the information we need to go ahead and sketch this guy. So let's see. I've got x-intercepts at just under 4. So again, it's just a sketch, so it doesn't really matter, but I'm going to come out here and plot them. So this will be -3.9, and this will be +3.9, or approximately. I've got a y-intercept at 0. And at, where'd they go? -3, I'm going way up here to 162, and then way down here to -162. And don't forget that I have a twist, so it looks something like this. Where should I start? And I'm also using what I know about polynomials in general, that this one's a degree 5 and it's a positive leading coefficient, so that tells me a lot about it, what it's going to look like. There we go. We got it. Okay, so all of this work is important. You got to show, you got to do some work to get things into factored form so that we start to analyze them. We got to show finding the intercepts, label the intercepts, make this statement, right? And then show our table listing our points and just sort of describing the type, and then use that to sketch our graph.